This video is for the revision of presenting uncertainties. First, we'll revise what is precision. Precision is how close are our results if we repeat the experiment. So it's to measure the random errors. So for example, this burette here, the result here is 43.60, and half of the smallest scale would be 0.05. So we put a plus minus here. It means that it could have been 43.65 or 43.55. So it's plus minus from 43.60. So that is random. That is random because we don't know what's the direction. We don't know whether it's plus or minus. It's just an uncertainty of this apparatus. If the apparatus is of high precision and we repeat the experiment and keep getting about the same results, then it means that there's very little random error. We can eliminate random errors by repeating the experiment a few more times. Then we get the average that will eliminate a little bit of the random error. So it can be improved by repeating the experiment. Accuracy. Okay, accuracy is how close is our results to the accepted results, or if we have a literature review. So if it's very close to the actual result, then it's very accurate. But if it's far, then it's not accurate. It might have been precise, but it might not be accurate. So accuracy is a measurement of the systematic error. If an experiment is accurate, then the systematic error will be very small. If we want to reduce systematic error, we might need to change the experimental method. Systematic error always comes in a certain direction. For example, in this usage of this burette. So if a person always overshoots, so there's a reaction time, we see a color change and we need to close the tab of the burette, and every time we overshoot and then we close the tab, so that will always give us a larger value than it actually is. So it's always that direction, always larger than it's supposed to be. So that is systematic error. We have 4 pictures here to illustrate accuracy and precision. So the first picture, we can see here that it's quite precise. We keep getting similar, close together values when we repeat the experiment, but it's not accurate because the true value is over here. So it's quite far from the true value. So in A, we have high precision, but low accuracy. Next picture, B. Okay, it's precise. The red lines are close together, meaning when we repeat the experiment, we get the same value again. And it's also very close to the true value. The true value is over here. So it's of high accuracy and high precision. Let's look at C. This one is not good because it's not precise. You can see that when we repeat the experiment, we keep getting a different value. It's quite far from each other. So repeating it, we can't reproduce the same results. And the other thing is that it's also not accurate. It's quite far from the actual value. So this is not so great. And picture D, we can see that it's, if we take the average value for the red lines, we might get this true value. So the accuracy is really not too bad, but it's not precise because when we repeat the experiment, we keep getting different values so far away from each other, meaning when we repeat the experiment, we can't reproduce the same results. So this is of higher accuracy, but lower precision. When adding or subtracting, we go by DP. And when multiplying or dividing, we go by SF. So if we have figures like this, so this is 3 dp and this is 2 dp and this is 1 dp, we have this answer. We will follow the one with the least dp here, which is 1 dp. So our answer should be presented like this, 25.3. So 1 dp. Okay, if you multiply or divide, so we have 3SF here, 4SF, 4SF. We have a really long figure in our answer. So this is 3, 4, and 4. So we're going to follow 3 as F. So our final answer should be like this. 2, 2, 2 is 3 significant figures. Okay, the next thing is in addition and subtraction, we add the absolute uncertainties, but in multiplying and dividing, we will add the percentage of uncertainties. So one is absolute, or add and subtract, and one is by percentage if we multiply or divide. Let's discuss this worked example from the textbook. Weigh out accurately approximately 100 grams of water in a polystyrene cup. So there's a polystyrene cup. Measure the initial temperature of the water. So initial temperature. Weigh out accurately approximately 6 grams of potassium bromide. Add that potassium bromide to the water. Stir and record the minimum temperature. And use the data that's given here to work out the enthalpy change of solution to appropriate significant figures. Let's try that. So we're going to use this formula. And the mole here is mass of KBr over its MR. Okay, so the first thing, we're going to calculate the mass of water. So we take the mass of the polystyrene cup plus the water, subtract the polystyrene cup. So since this is subtraction, so we're just going to sum up this uncertainty. So that's the absolute uncertainty. We do need to calculate the percentage of uncertainty because we're going to do some multiplying and dividing later. So convert that to percentage of uncertainty first. As for the mass of KBr, so we're doing subtracting again. Therefore, we're going to sum up the uncertainty again. So subtraction, sum up the uncertainty. We're going to convert that to percentage of uncertainty again. Change in temperature, again, is a subtraction here. So we sum up the absolute uncertainties. And then we convert it to percentage of uncertainty, the same way again. Next, we're using this formula. So MC change of temperature. We're doing multiplication here to get the joules. And as for the moles, we're going to take the mass over the MR to get the moles. So the energy in joules per mole, that's what we did here, will give us the answer in joule per mole. We're going to convert it to kilojoules per mole here. So divide 1000. Since there's a temperature drop, so it's endothermic, it's a positive value. Okay, the uncertainty is actually, so we have 9.5 here. And I can total up this 0.3 and 0.02. So that 0.32 is actually of little effect on the uncertainty because 9.5 is a pretty huge figure. So these 0.32% is actually negligible. Even if you total it up, you're going to get a very similar answer because it's so small. So we're going to ignore that 0.32 here, and we're just going to use 9.5 multiplied by our answer here to get the absolute uncertainty. Since the uncertainty is 2, that's to one significant figure. So the value could be higher by 2 or lower by 2, which means that 0.15 actually brings no meaning. This 0.150 brings no meaning to the figure since the uncertainty is right now plus or minus 2 kilojoule per mole. So we're just going to quote it as 17 and plus minus 2 kilojoules per mole. Now let's compare using 9.5 and 9.82. So that 0.32, let's see what it does. So 9.5% out of 17.150, that would be 1.62925. And 9.82% out of 17.150 is 1.68413. So it's still 2 is the uncertainty to one significant figure. So in the end, we're still going to get 17 plus minus 2 kilojoules per mole.